let's talk about introduction to logarithms. So let's answer the main question. What is a logarithm? One way to think about logarithm is that it answers a question like this. How many of one number do we multiply to get another number? For example, how many trees do we need to multiply in order to get 81? When you answer a question like this, then you are finding the logarithm. We know that if we multiply 3 times 3, we get 9, times another 3, we get 27, times another 3, we get 81. So that means we are going to multiply 3 4 times so that we can get 81. And the shortcut way of writing repeated multiplication is to write that as an exponential number. So we write this as 3 raised to 4 equals 81. Now this number 4 is now what we call as the logarithm. You might be complaining, 4 is the exponent. You're right, because logarithm means exponent. So we had to multiply 4 of these number 3's in order to get 81, and this 4 is now the logarithm. So that if you have 3 raised to 4 equals 81, we can write this in logarithmic form this way. We write the word log for logarithm, and we get the base. The base of 3 raised to 4 is 3. So we now say the logarithm to the base 3 of the power 81 is equal to the exponent 4. So from exponential number, if we want to express that number in terms of the exponent 4, that means we want to solve for the exponent explicitly, then we write the log of the power to the base. And here, the logarithm of 81 to the base 3. Another way of reading this is the logarithm to the base 3 of 81 equals 4. So notice now the relationship. The base 3 becomes the base of the logarithm, the exponent becomes the number that's isolated, and the 81, which is the power, becomes this number. So that if you do not know this left side, if you are just looking at the logarithm of 81 to the base 3 equals 4, then you get this base 3, and you get that exponent 4 that is equal to this 81, so that you can go back to its exponential form. Do you know that the word logarithm is made up by Scottish mathematician John Napier? Logarithm came from two Greek words, logos, meaning proportion or ratio, and arithmos, meaning number. So together, they mean ratio number. But for our understanding, it's easier to remember logarithm as exponent. Logarithm means exponent. So when you have cases where you do not know the exponent and you are solving for the exponent, you are going to use logarithm to solve for that exponent. I remember in high school, before I learned about logarithms, whenever I see this log and ln symbols in scientific calculator, I feel a little bit terrified. It seemed to me that the word logarithm is a very mysterious word, only to find out later that logarithm just means exponent. So nothing to worry, nothing to fear about this big word logarithm. Now, there are instances when you can encounter a logarithmic form like this. The logarithm of 100 equals 2. The base here is not specified. In cases like this, it is implied that this is the same as the logarithm to the base 10 of 100 equals 2, where the missing base here is implied to be the number 10. So if you want to write now this in exponential form, we now start with the base 10, and the exponent is the number that is isolated here. So the exponent is 2, that is equal to this number 100. So 10 times 10 equals 100. You might also encounter a case where you see this symbol ln. ln of 50 equals some numbers. ln is the same as the logarithm to the base e of whatever is the number next to it, equals this number 3.912. So ln is the same as log to the base e. ln is a shortcut way of writing log to the base e. So if you want to write this in exponential form, we now therefore write this as the base e raised to the exponent 3.912 equals 50. Why is the base e important? There are at least two reasons among the many reasons why e is important. First, the exponential function y equals e raised to x has that characteristic that at any point, the slope of e raised to x equals the value of e raised to x. Finding the slope of the line tangent to the curve enables us to study the mathematics of change. Also, the number e is important because the exponential function y equals e raised to x also has that characteristic that the area under the curve from the left side going to any point x is equal to the number e raised to whatever is that number. So we now say that the derivative of e raised to x is equal to itself, and the integral of y equals e raised to x is also equal to itself. So let's target now our first objective, that is to convert from exponential expression to logarithmic expression and vice versa. So rewrite in exponential form the logarithm to the base 6 of 36 equals 2. So the first thing you have to identify is what is the base. The base is 6. What is the exponent? The exponent is the number that is isolated here. You have 2, and that is equal to this remaining number, 36. As easy as that. Okay, number 2. Rewrite in exponential form the logarithm to the base 14 of 1 over 196 equals negative 2. Just do it step by step. Start with the base 14. The exponent is the number that is isolated. So you have negative 2 equals the remaining number, 1 over 196. Now remember that when you have a number raised to a negative exponent, you can write that in positive exponent by writing this way. You write 1 over, copy the base. Now, the exponent is positive. So 14 raised to negative 2 is equal to 1 over 14 raised to positive 2 equals 1 over 196, which is true because 14 times 14 equals 196. Now, let's reverse the process. This time, we have a number in exponential form. We are going to rewrite this in logarithmic form. So you have 64 raised to 1/2 equals 8. So to rewrite this in logarithmic form, you start writing the word log, identify what is the base. The base is 64, and then the number on the right here is 8, that is equal to the exponent 1/2. So the logarithm to the base 64 of 8 equals 1/2. Another one. Rewrite in logarithmic form. 1 over 12 raised to exponent 2 equals 1 over 144. Again, start with the word log. The base is 1 over 12. The power is 1 over 144 equals the exponent 2. Okay, rewrite in logarithmic form. 1 over 5 raised to the exponent x equals y. So again, write the word log. Identify the base, 1 over 5, and then copy y equals the exponent x. So the logarithm of y to the base 1 over 5 equals x. Okay, rewrite in logarithmic form. We write this as the logarithm, the base is 6, copy this x, and then copy the exponent y. As easy as that. Now, this time, let's go to skill number 2, evaluating logarithmic expression. When we say we are going to evaluate, that means we are going to find the exact value or compute the value. What is the value of the logarithm to the base 4 of 64? We do not know the value of this, so let that value be equal to x. Writing this now in exponential form, the base is 4, the exponent is x, and that is equal to 64. This means how many times should we multiply 4 by itself in order to get 64? Now take note that 4 times 4 equals 16 times 4 equals 64. So that means 4 raised to the third equals 64. So this means we can rewrite this as 4 raised to x is equal to 4 raised to the third power, because 4 raised to the third equals 64. So from here, when the base are the same, then the exponents are also the same. So we know that x is equal to 3. So therefore, the value now of the logarithm to the base 4 of 64 equals 3. And this means that we need to raise the base 4 to the exponent 3 so that we can get the power 64. Let's have another one. Without using a calculator, evaluate the logarithm to the base 6 of 1 over 216. Since we do not know the value of this, let that value be equal to x again. And then we can form this exponential equation. 6 raised to x is equal to 1 over 216. Now, since you have a fraction here, we can write this also as 1 over 6, this time raised to a negative exponent, equals 1 over 216. So that we have the same form, 1 over certain expression, 1 over certain expression. I want you to notice that from positive exponent here, the sign becomes negative when I write that as 1 over the base raised to that exponent. The sign becomes negative. So let's rewrite 216 as 6 raised to certain exponent. We know that 6 times 6 equals 36, times 6 equals 216. So we know 6 raised to the third power equals 216. So from here, we can now write this as 1 over 6 raised to negative x equals 1 over, instead of 216, we have 6 raised to the third power, 6 raised to the third power. From this form, it's very clear that 1 and 1 are equal, 6 and 6 are equal. For this equation to be true, then negative x must also be equal to this number 3. So therefore, negative x equals positive 3, which means x equals negative 3. Okay, let's have another one. Evaluate the log to the base 64 of 4. Since we do not know the value of this, let's equate this to a variable x. So this means 64 raised to the exponent x is equal to 4. Notice that 64 is equal to 4 times 4 times 4. So 64 can be written as 4 raised to the third power. So therefore, instead of writing 64, we can write this as 4 raised to the third power raised to x equals 4. Now, using the property of exponent, power of power, we can multiply the exponents here to get 4 raised to 3x equals 4. Since there's no number here, it's implied that the exponent of the number 4 at the right is 1. Since the bases are the same, the exponents must also be the same. We can now therefore say that 3x is equal to this number 1, and solving for x equals 1/3. So the value therefore of the log to the base 64 of 4 is 1/3. Now what's the value of this? You have 12 raised to the logarithm to the base 12 of 144. Again, since we do not know the value of this, then let's equate this to x. Notice that this is an exponential form with 12 as the base. This entire expression, log to the base 12 of 144, is the exponent. This is the exponent. This is the base. And this is the power. Writing now in logarithm, we can now write the log to the base 12 of x is equal to the exponent log to the base 12 of 144. So notice now the form, log 12, they're the same. So that means x must be equal to this number. So we know that x is 144. And since we equate this expression to x, then this entire expression is 144. Let's have one more problem. What is the value of x raised to log to the base x of 72? Now, since x is the variable that's used here, let's try using a different variable. Let's equate this value to, let's say, a. Since this is an exponential form, we can rewrite this in logarithmic form. So we write this as log to the base x of a is equal to the exponent log to the base x of 72. So log x, they're the same. That means a must be equal to this number, 72. So a equals 72, which means that this entire expression is 72.